Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Mark Liberman, who's a professor of linguistics and computer and information science at the University of Pennsylvania. His many research interests include phonetics, information extraction, language evolution, and speech. He is the founder and director of the Linguistic Data Consortium. Welcome, Mark.
Good to be here.
I want to start with your paper on human language technology, in which you say human language technology encompasses a wide array of speech and text processing capabilities. The Defense Advanced Research Projects agencies, that is DARPA, are pioneering research on automatic transcription, translation, and content analysis were major artificial intelligence success stories that changed science fiction into social fact. During a 40-year period, 10 seminal DARPA programs produced breakthrough capabilities that were further improved and widely deployed in major popular consumer products, as well as in many commercial, industrial, and governmental applications. Could you give a little bit of a history of human language technology?
Well, there's a long period of technology that didn't work.
Yeah.
Claims, originally probably quite dishonest claims. There was a man in the early 20th century who claimed to have developed a voice typewriter that worked by electromechanical means, and of course didn't work. But then in the 1950s and 60s, there were lots of engineers who thought that they could solve the problem using resonant circuits and computers and analog digital combinations and so on. And they made small amounts of progress, but basically the techniques didn't get very far.
Yeah.
And by the middle of the 1960s, a man named John Pierce, who was an executive at AT&T Bell Telephone Laboratories, came to the conclusion that it was all nonsense, and that efforts to invest in such things were really throwing good money after bad. And he chaired a committee for the National Academy of Sciences on machine translation, and then he wrote a sort of opinion piece for the Journal of the Acoustical Society of America called Wither Speech Recognition.
Yeah.
And in both of those, he argued that the science wasn't ready to support technology in this area. And he had a lot of credibility. Also, he was correct about the fact of the matter in those days. And so in the United States, for a fair number of years, there was very little, and then for a period of time, no government investment in human language technology construed broadly, which would include machine translation, speech recognition, speech synthesis, and so on.
Yeah.
And relatively little investment on the part of American industry, although there was definitely some. There were people at IBM, for example. There were some people at AT&T, some people at Texas Instruments, and so on. Then things changed in the middle of the 1980s. And some people in the government decided that this was just too important to let it go without trying to move it forward.
Yeah.
And so they decided to begin investing, first in speech recognition, and then a little bit later in machine translation, and then in a variety of other technologies.
Was the early objectives more military objectives, or not really? It's more fundamental research.
Well, I think because it was DARPA,
yeah,
because it was the Defense Department, there was always a kind of idea that have applications of interest to the military.
Yeah.
So one of the very first projects was something called resource management, where the idea was that you would be able to give verbal commands to a system about how to move military resources around.
I see. Okay.
Or military relevant resources around.
Right.
And it was a long ways from being practical. It was really just a toy system. But still, it was a pretend military application rather than a pretend civilian application.
Yeah.
There were other kinds of cases that were, I think, much less pretend. For example, there was an interest in the possibility of speaker recognition that was quite explicitly oriented towards the possibility of recognizing terrorists on cell phones and so on. That is, could you, if you have some samples of someone's voice, can you pick their recordings out reliably at all from 100,000 others?
Yeah, so in the mid-'80s, I would imagine, obviously the volume of data that we were dealing with wasn't great, but I guess, looking forward, they were thinking if we can automate the whole thing, perhaps it can then create red flags on items.
So there were two things relevant to that worth saying. One was the tradition in especially military-funded but government-sponsored projects in general was that the deliverable, so to speak, or the evaluation was either published papers or demonstrations.
Right.
This was evaluation by demo, and it would be a demo to, some visiting committee of high-ranking people, whether civilian or military, who would be given a kind of structured exposure to what the systems were supposed to do.
Right.
And that can work reasonably well when what you're showing off is a fighter jet.
Right.
I guess that's not an area where I'm expert at all. But it's not a very good way of evaluating software in artificial intelligence or anywhere else. There was one famous example, not a DARPA demo, but a demo at a conference where everything had been scripted. That is, the speaker was supposed to give a series of commands or questions, and the system was going to respond, and they got out of sync so that the system was responding not to the question that was asked, but the question was going to be asked.
Right.
That was embarrassing. I think the previous DARPA demos were not that bad. the people who put them on were not actually dishonest, but still, it's easy when you're setting up a demo and you know what's going to happen to script things in such a way that it looks impressive without actually really working very well.
Right, right.
And so anyway, what the people running the human language technology programs at DARPA decided from the 1980s onward is that every program, every task would have a well-defined quantitative evaluation, which would be described in detail at the beginning of the program, not at the end, would be carried out automatically by software, and would be administered by a neutral third party, namely the National Institute of Standards.
Some sort of error rate?
Yes, well, or some sort of cost function or error rate or success rate, or what doesn't really matter. There would be discussion and debate, and they would settle on, all right, the metric that we're going to use is word error rate, or the metric that we're going to use is, speaker recognition F measure, something like that. And here's how we're going to define it. Here's the program that's going to calculate it. And all that is made very precise and worked out in advance. Now, one consequence of that is that you're now in a situation, certainly in human language technology, but in AI in general, most areas of AI in general, of making decisions under uncertainty. You have imperfect information, partial information, but you have to make a choice. You have to make a decision. You have to do a classification. You have to make a transcription, whatever. And that kind of decision-making uncertainty is, of course, exactly what led to the development of probability theory hundreds of years ago.
Right. Yeah.
And so this way of approaching things obviously valorized the classical kind of machine learning, which is basically statistical model fitting. So there was a turn in the 1980s, 1990s away from sort of hand-coded programs by people who saw intelligence as applied logic to fitted machine learning models by people who saw intelligence as applied statistics.
So from sort of rules-based expert systems into more what is now called machine learning, but really fancy way of saying statistical models.
Yes, exactly. Yes, exactly.
Yeah.
And of course, it's also the case that that approach also valorizes data.
Right.
Because if you're trying to train models to solve your problems, the more data you have, the more accurate your models are, or more relevant data you have at least, the more accurate your models are likely to be. And of course, speech and language are in principle, very, very difficult things to model. A language has lots of words, there are lots of speakers, there are lots of circumstances of recording. If you're dealing with telephone speech, there's lots of transmission channels. There's lots of topics people could be talking about. There's lots of languages in the world.
Right.
And so as the people at IBM used to say, there's no data like more data.
And so were you at Carnegie Mellon at this point, or that was afterward?
No, I was at Bell Labs.
Okay.
From 1975 through 1990. And then I moved from Bell Labs to University of Pennsylvania. I actually had a job offer from CMU, but I went to Penn instead. But I certainly knew people and know people at CMU. As well as other places that have been involved in these efforts. So one other thing that happened, again, in the 90s and early aughts especially, is that the people running the DARPA Human Language Technology programs, and there were quite a few of them focused on different aspects of the problem, just made an important consequential decision, which was to open up these evaluation campaigns, to open up these challenges to anyone who wanted to participate. So the idea was that the data could be made available to whoever wanted it. The evaluation programs, the scoring programs, could be made available to anyone to use to develop their system. And anyone who wanted to could come to the workshops where the National Institute of Standards would score competitively all the different entrants and put up the leaderboard, so to speak, say who won. So they realized they were onto something in one early, this was before the internet existed, before Google was founded, and a woman named Donna Harmon at National Institute of Standards, especially interested in the problem of document retrieval, which is basically like Google. Now, people had been working on document retrieval, digital document retrieval, since the 1960s, but it had never really been practical, and the evaluation domains in which they worked were rather small, with hundreds of documents, or at most maybe order of magnitude of 1,000 documents. And Donna's idea was, okay, let's see if we can do this at scale. Let's see if we can do this for 1 million documents. So where are we going to get 1 million documents? And this was before the internet. This was before Google. Nobody had 1 million documents. So we started poking around trying to find documents. And then Peter Brown, who was then at IBM and who is now the CEO of Renaissance Technologies, actually, if you've heard of them. But he learned that IBM had been subscribing for a long time, for decades, to the Federal Register, which is this government-published listing of programs and results and calls and so on. Policies, perhaps. I don't really know what's in it now. And they had this, in those days, of course, because this was before the internet and so on, this had been arriving at their location on 9-track tapes, you know, those big tapes the size of a dinner plate, that people used to spin on those big machines, the size of refrigerators. Each one of them held, I think, 250 kilobytes.
Wow.
So anyway, he called me up and he said, you know, I hear you guys are looking for data. How about, you know, whatever it was, 20 years of the Federal Register? And I said, great, okay, give it to us. So a couple of days later, a semi-truck pulled up our building at the University of Pennsylvania, and people began wheeling out these cardboard boxes full of these 9-track tapes. And luckily, we just started a new institute, and we'd moved into a new space, and we had some unused offices. So we put these boxes into 2 offices. It filled the offices from floor to ceiling, fairly large offices. And then the building manager found out about it and got upset because it turned out that this was exceeding the floor loading for the building. So we had to spread them out. Anyway, I will not give you the whole elaborate story of how we actually turned those into real data and how we distributed them, but we managed it. Anyway, this was a very attractive thing. There were a lot of people who thought that, who foresaw that this was this was going to be important in the future. And so the government program that aimed at developing document retrieval techniques at scale, I think they paid 4 performers, as they called them, gave them contracts to work on it. But when they had their meeting, they got 40 groups who came and competed for free. who worked on the problem, and I think the top scoring groups were not among the ones they paid.
Okay.
So they realized, gee, this is a pretty good deal. We can define a problem, pay for some data, make the data available, define a task, define a metric, publicize the challenge, and we can get people to work on this problem even beyond the ones that we pay.
Right.
And so that has been the practice that they followed for 30 years or so since then.
Yeah, much more efficient. It allows competition, and it allows the best to rise to the top.
Well, the one thing they did insist was that the cost of the price, the entry price for participation, was that you had to come to the workshop and you had to tell people in a responsible way what you did.
Oh, okay.
They didn't let people publish their code, but they did ask them to say in detail what they did and how it worked and what aspects of it worked and what aspects didn't work. So the result of that was that participants in these programs and people even not participating in the programs, they would adopt the things that worked and discard the things that didn't.
Yeah.
Now, this is kind of hill climbing in a complicated technical space.
Right.
So sometimes an innovation that doesn't work when you're in one place would have worked if you were in a different place in the development. But the analogy that I use here is the analogy to the development of automobile technology. So if you look at automobile engines today and compare them to the automobile engines of, say, 1910 or 1915, and ask what's happened, well, from one point of view, they're just enormously better. They're more powerful, they're more efficient, there's more power per weight, they last longer, and they're cheaper to make, relatively speaking, and so on.
Yeah.
If you ask why is that true, there was no one single invention. There was no brilliant idea, no sudden discovery of an equation that solved all the problems. Instead, it was 1,000 small innovations in metallurgy, in design, in manufacturing, and so on. And that's also what happened in human language technology. The difference between the speech recognition that didn't work in 1980 and the speech recognition that works pretty well, although not perfectly today, is not one thing.
Yeah.
It's 1,000 things.
So,
lots of little changes.
Approximately what time frame, Mark, we had something that is reasonable that commercial companies gotten interested in?
Well, from the very beginning, there were companies who were interested in these technologies. So IBM, for example, was interested from the beginning.
Yeah.
As the internet grew and so Siri, for example, was actually originally spun off from one of these DARPA programs. There was a DARPA program that was aimed at producing a sort of soldier's assistant. And one of the performers on that project, so the idea was that there would, the warfighter would have a microphone that they could talk into, and they could ask questions and get answers and give commands and have things done, give instructions and have things done. And this could be integrated across multiple people, perhaps. So one of the groups contracted to work on that was at SRI, Stanford Research International, I guess it's called. I guess that's what the acronym stands for. And so after that program ended, and unfortunately that program never produced anything that the military was able to use or to use. They had a real problem with the next step, with sort of handing off to development there, at least in that case. But so that group spun itself off from SRI and started creating and marketing this voice assistant named Siri.
Yeah. When was that? That's
and Apple bought them, and then the rest is history.
So when was that? Late 90s or early 2000s or something like that?
That would have been early 2000s, I guess.
Okay.
I don't know. You could look it up.
Yeah. And so essentially DARPA invested quite a bit into this foundational technology that basically then expanded into commercial applications at Apple, Microsoft, IBM, and elsewhere, right?
Google, yeah, sure.
Yeah. And it has been improving since then.
Yes, well, so for many of the basic technologies, the government feels that they don't need to invest anymore because that role has been taken over by the Apples and Googles and IBMs and Microsofts of the world.
Yeah.
And I think that's true to some extent. There are some kinds of problems that those companies have not as yet really been addressing. And also there is the difficulty that unlike, well, Google, for example, has been pretty good about publishing some of the data that they use so that other people can, so that research can continue.
Yeah.
And similarly, Amazon and Facebook have published some data and some code that's been helpful. Yeah, and as you probably know, DARPA has kind of changed its focus in the area of artificial intelligence into sort of going back to ideas of understanding and adaptation and things that we would think of as being more intelligent and less, as the
mechanistic
phrase goes, cat detectors.
Yeah, I mean, artificial intelligence, as you know, has become very confusing. A lot of the technologies that we see and hear are actually automation, not necessarily AI. And so,
right. Well, lots of them are sort of digital pattern recognition, which is based on the idea that you have very, very large amounts of data of the kind that you are going to have to recognize patterns in. You have lots of training examples where the patterns are named or annotated. You have some idea of how to expand that astronomical amount of data by adding noise and distortion of relevant kinds. And you have, warehouses full of computers who can churn away and develop the systems that are going to do the pattern recognition. And that's very successful in many applications.
Yeah, I want to go into a couple of your papers that are, related to life sciences. So one of them is automatic classification of primary progressive aphasia patients using lexical and acoustic features. And so you say two variants of primary progressive aphasia, PPA, are subtypes of frontotemporal degeneration, FTD, which is the most common type of dementia among individuals under 60 years of age. And using a classification scheme of linguistic features from digitized speech samples, you showed that you can actually do this in a diagnostic setting, right? You want to talk a bit about that?
Sure. Well, more generally, there are a number of areas that are decades behind the times in terms of the kind of technology that we've been talking about.
Yeah.
And medicine is certainly one of them.
Yeah, there's a lot of resistance there for sure. Yeah.
Well, there's reasons for the resistance, but part of the resistance goes beyond the reasons. Another is education.
Yeah.
And the third is law. There are others as well, but those are big, medicine, education, and law. I don't know if you add them up, you must be getting to close to half of GDP. I don't know.
Yeah, that's true. Medicine alone is about 20% of GDP. Yeah,
right.
Yeah.
And education is pretty big, depending on how you count it, and lawyers a lot of GDP in all areas. But anyway, so the work that we've done on, the term that people use for such things now is digital biomarkers. And biomarkers is a kind of a fancy word for features.
Yeah.
But biomarkers started out in chemicals and stuff like that.
Yeah, in pharmaceutical R&D,
but
it's really a proxy.
If you call features of speech or features of gait or features of gaze or something like that, behavioral features, biomarkers, it makes it seem more scientific, apparently. But the idea that there are symptoms for various mental and neurological disorders in speech and language is not a new idea. People have, neurologists and psychologists have been using speech and language features diagnostically for probably thousands of years, but certainly quite explicitly since the middle of the 19th century.
Yeah.
And there are both standard sort of informal bedside examination techniques that are based on speech and language. And there are also slightly more formal, slightly more modern, slightly more quantitative, though still generally pencil and paper, cognitive tests developed in the 40s, 50s, 60s, 70s that people give in order to get a score that's going to go figure into the final diagnosis.
For dementia and things like that, right?
And things like that, yes, exactly. And so one thing that's very obvious is that it ought to be possible to automate aspects of the traditional subjective sort of bedside evaluation. But it also ought to be possible to automate these pencil and paper cognitive tests, because most, not all, but a majority, I think, of the tasks involved in those tests are actually speech mediated. So, I mean, there are things like digit span, can you repeat back a string of digits? So-called logical memory, where you're told a story and asked to retell it. And so on. Picture description, where you're shown a picture and asked to describe it.
Yeah, it became, as you know, it became quite famous recently.
Yes. Yes, man-woman TV. Actually, I think that's free recall or something. Anyway, it has a different technical name.
Yeah.
But it's clear that even within the scope of the standard cognitive tests like free recall and digit span and story retelling and picture description, there's actually lots of information besides the things that the pencil and paper scoring counts.
Yeah.
There are things having to do with the distribution of speech and silence segment durations, pitch range, speaking rate, word frequency, word familiarity, sentence complexity, et cetera, et cetera, et cetera.
And there is, you say in the paper, Mark, there are two types of PPAs, right? There is a semantic variant and the non-fluent agrammatic PPA. And essentially you expect different things in these two conditions, right?
Yes, I think the most interesting thing about that work, well, I don't remember whether we featured it in that particular paper, but has been discussed in other papers. There's a kind of frontotemporal degeneration called behavioral variant.
Oh, yeah. It's not here, but I saw that elsewhere. Yeah.
Yeah. Well, so behavioral variant the sort of canonical example of what it causes behavioral disinhibition. So someone with behavioral variant FTD might walk into a restaurant, see something on a stranger's plate that attracts them, reach over and pick it up and put it in their mouth.
Right.
Which is, you know, an impulse that we all might have, but the rest of us would suppress the impulse.
Yeah.
So that kind of disinhibition is apparently the sort of characteristic symptom. And the general story about behavioral variant FTD was that it didn't really have linguistic characteristics. And one of the things we found was that if you measure more subtle aspects of the way people talk, there actually are diagnostic aspects in speech, which is not surprising because actually these diagnostic boxes, there aren't really bright lines that separate them. They kind of tend to shade off into each other, and there are somewhat more diffuse behavioral results. Apparently, I'm not a neurologist, so take that for what it's worth. But anyway, the thing about that, about all of that work, the paper that you cited and other papers of that kind that we've done, is that we're operating under a kind of a handicap because we have relatively little data compared to other areas of speech and language technology. There is no DARPA here. The National Institutes of Health, as I said, is 30 years behind the times.
Yeah. No truck arriving for this.
If they understood this, if they understood what was really happening, they would do the same thing that DARPA did in the late 80s, early 90s. They would say, okay, we're going to get, you know, 20 or 30 or 40 sites to collaborate on gathering data in a harmonized way, in a standard way. We're going to combine all of the data suitably anonymized. We're going to share the data with appropriate safeguards. Of course, we're going to get informed consent from the subjects. We're going to withhold some of the data so that people will develop their diagnostic tools on part of the data, and then they'll have to apply the technology, apply the algorithms to data that they haven't seen, and we'll have a neutral third party like the National Institute of Standards supervise the leaderboard, you know, look to see who scored what.
And you had, in the paper, you described a test with 100 subjects or so?
Well, so the Frontotemporal Degeneration Center at Penn has been collecting picture description data from their patients for, I think, about 15 years, and they have about more than 1,500 recordings.
Yeah.
So that's a fairly large data set, although if you ask, you know, how many of them one diagnosis as opposed to another, then you start getting down into 100 or 150 or even fewer. And when you want, if you want subjects who have longitudinal recordings, that's also a smaller number. There are now starting to be some bottom-up gatherings, some bottom-up organizations of consortia in the Latin plural, of centers that are getting together to try to pool data, and I'm hoping that will happen. It's not being driven from the top down, it's coming from the bottom up.
So my own understanding, so the picture description data, so you're showing somebody a picture, this is like the cookie theft picture or something like that, and then you're recording what that person says for a period of time?
Yes, the usual way it's done is you tell them in advance that people take about a minute or a minute and a half to describe the picture.
Yeah.
But you don't give them a time limit. You just let them talk as long as they want. When this is done interactively, the interviewer very often encourages the subject if they kind of run out of steam after 15 or 20 seconds. You know, and they say, what else do you see there? Or is there anything else you can say? Or, you know, stuff like that.
Right.
We've been gathering data online at speechbiomarkers.org for picture descriptions and what's called fluency, which is like how many words starting with F can you think of in a minute. And we have, I think we now have 1,804 sessions, 1,804 sessions.
Yeah.
From a variety of people, but I'm hoping that we can advertise this more broadly and get 5,000 or 10,000.
Yeah, it makes it more powerful then. So these acoustic features in the paper, you say, some examples are the mean duration of speech and pause segments, total pauses, total speech time, pause time, and so on. And so this can all be picked up. These features can be picked up automatically, right, when somebody speaks?
Absolutely. So the speech segment and silent segment duration, we have a good speech activity detector that seems to work pretty reliably, even on recordings that are not of the highest quality.
Yeah.
We would like, as you mentioned earlier, we have lexical features like word frequency and number of different words and word familiarity and stuff like that. That depends on having a transcript. And I'm sorry to say that at the moment, current speech recognition technology is not really quite good enough. It's certainly nowhere near good enough when the recording quality is less than optimal, which is not infrequently true. But obviously, if everyone is describing a particular picture or thinking of words that start with F or names for animals or something like that, this constrains the sorts of things that they're likely to say very strongly. And so we believe that with a reasonable amount of training material to adjust the language models, as they call it in the trade, that we'll actually be able to automate the transcription adequately as well.
Yeah, and so it's fascinating, Mark, that you could actually, with very high accuracy, have a diagnostic against the control with either one of those PPA varieties. And then you also tried to sort of look at between them, right? Whether you can differentiate between semantic PPA and the non-fluent PPA. And those, the expectations there, appears quite different. So the semantic PPA, people make there are deficits in a single word use, whereas other one, it's more about the speech rates and so on, right? So
yeah.
So between head-to-head comparisons between these two conditions, it's more difficult. Looks like against the control, we could say there is an issue, but head-to-head between these two, I guess you need a little bit more data.
More data, maybe better features.
Better features, yeah.
It's important to note that in addition to dealing with relatively small amounts of data, that is, even in the early days of human language technology speech recognition, we were dealing with tens of hours of speech, and very soon with hundreds and thousands and tens of thousands of hours. In this case, each picture description is about a minute long.
Yeah.
And so if we have 100 picture descriptions, or let's say 50 for one category, that's less than an hour.
Right.
And so we definitely need more data. But it's also the case that what we're working with here are relatively simple features. They're kind of the first simple things that came to mind. And we want to demonstrate that these simple ideas can have some power. There are other kinds of techniques that would be more sophisticated, and some of them just require more data. So, for example, it's likely to be the case that the choice of words in describing a particular picture is relevant for the semantic semantic dementia.
Yeah.
But we don't really have enough examples to have a very good statistical model of what words are likely to occur and what words are not likely to occur.
Yeah, and that depends, I would imagine, a lot on initial conditions, right? A lot on education, a lot on the individuals.
Yeah, well, those would be covariates. Those would be
Yeah.
additional variables that we would allow for in the statistical model. But obviously, education matters, age matters, and of course, what picture they're describing matters.
Yeah. No, I find it, really fascinating that there is a difference in the use of nouns and pronouns between the two conditions. uh, and so, as you know, the home health arena is really taking off. And so, your experiment already shows fair amount of power from a diagnostic perspective. If we can pick up these types of issues earlier, and this could be, something quite simple that could be administered at home, and if the machine can, with fair amount of accuracy, raise a red flag, that could be quite useful, right?
I would hope so. At the moment, with these various kinds of neurodegenerative disorders, there are no cures.
Yeah.
As you probably know, there have been any number of drug trials, basically all of which have failed, although there's some underway now that haven't failed yet, I believe.
Right.
And there are different theories about that. One theory is that they failed because they're attacking the wrong physiology.
Mm-hmm.
That the physiology that they're trying to deal with is actually a symptom and not a cause.
Right, right.
And that could be true. But another possibility is the notion that they're just intervening too late.
Mm.
That by the time someone is diagnosed with Alzheimer's disease, or for that matter, frontotemporal degeneration, their brain has been degenerating for some time, maybe a decade or more.
Right. So,
and it may just be too late to intervene.
Yeah.
So the idea is that if you could detect a problem early, which means that you're detecting, as you mentioned, for example, education and just general verbal ability and so on, have a big effect. So we don't want to use a low threshold and say, well, you have to get below this threshold before we flag you.
Mm.
Instead, we would like to look at the slope of change,
right,
the rate of change in your performance. And if the slope is steeper than somewhat, then that raises the red flag. And then maybe you start taking an experimental drug.
Yeah.
Now, whether that can work, we can only hope.
Yeah, but in a repeated experiments, though, Mark, I would imagine there are other things you need to worry about, right? An individual could get conditioned to get better over time in repeated experiments, possibly.
Yes, well, that's why we want longitudinal data, because we want retest reliability. We want to know to what extent there are practice effects.
Yeah.
I think it would be a big mistake for many reasons to give people exactly the same test. You don't want to describe the same stupid cookie theft picture,
right.
Every week for 10 years.
Yeah.
It's going to get boring aside from practiced pretty quick. And in fact, you probably don't want to use that picture, because that picture is a kind of, white bread American suburban 1950s kitchen.
Right, right.
And it doesn't apply in the lives of very many people, a very large proportion of the population these days. And in fact, when we gave that picture, along with some other pictures of a more modern kind that we had created to undergraduate students last spring, a large proportion of them sort of commented on the social background.
Mm.
They said, gee, that's not what kitchens are like anymore.
Yeah, but the staying power of that picture is quite amazing. It's almost 100 years old, right?
No, I don't think so. I think it's from the 50s or 60s.
Oh, okay, yeah.
No, it wouldn't be 100 years.
70 years, yeah. But still being used. I want to touch on another paper along the same lines, entitled Lexical and Acoustic Characteristics of Young and Older Healthy Adults. And the study examines the effect of age on language use with an automated analysis of digitized speech obtained from semi-structured narrative speech samples. So this again, if we get really good at this, we could have an expectation of a subject based on that subject's age, and perhaps we could measure deviations from it.
Right. Well, so we really don't know, because we don't really have normative data,
Yeah.
What normal aging looks like in studies of the kind, quantitative studies of the kind that we also don't have, right? So there is no way to give a longitudinal digital biomarkers task for which we have sort of reliable normal aging statistics.
Right.
I'm exaggerating a little bit because there is some of that out there, but we're not nearly ready. What ought to be within reach, what we ought to be able to reach out and grasp, is an internet administered, browser-based test battery that would not take very long, that could be completely automated both in administration and scoring, that people could do by, just like they wear a watch around their wrist to keep track of their steps and their heart rate.
Right.
Well, actually, I suppose they might talk into the watch, except you can't show the picture or whatever, but they could do it on their smartphone.
Yeah, absolutely.
And combine it with other things. I mean, there are actually good digital biomarkers available from gait, which is easy to measure with a watch or a smartphone, and plenty of other things as well. That would then be integrated, and then, just as you can look at a graph of what's been happening with your resting heart rate, or look at a graph of what's been happening with how many steps you walk or whatever, over the last year or 2 years, you could look at a graph of what seems to be happening with your neurocognitive health.
Right.
And as I said, I think that ought to be within reach, but we can't do it now.
Yeah, I mean, the beauty of this, Mark, is that, so if you think about the watch and other instruments that are coming out, we are measuring a lot of, sort of physical activity, cardio health, those types of things. There is almost nothing that continuously measures cognitive aspects. And if something like this is possible, this is a very low cost activity, right? It just
ideally, I mean, we've been using the versions of the tasks that neuroscientists, psychologists, and neurologists have been using for more than half a century, because we want to persuade them. But one of the comments that we got back from the people doing test versions of these tasks is that they're not a lot of fun. And I mentioned this to the head of the Penn frontotemporal degeneration. He said, well, neurologists are not into fun. And unfortunately, that's true. But in fact, the right thing to do would be to gamify this. That is, to make tasks something you could do that would actually be, interesting, and you would almost want to do it just because it was a fun way to pass 10 minutes.
Right.
And you could certainly get, neurocognitive measures out of that sort of thing over time. You need to norm it for practice effects and for normal aging and for comparison to standard tasks and so on. But I would predict that 5 or 10 years from now, that's what people are going to be using.
Yeah, and you could possibly generate random pictures too, because these are acoustic features that are being studied, and so the picture itself should not really matter, right?
Oh, absolutely. So we've actually started experimenting with generating random pictures.
Yeah.
In which you have an inventory of objects and places they can be, and also if you want to do on small screens like smartphone screens. Rather than having a large, complicated picture, it's probably better to have a simple animation.
Oh, that's right. Yeah.
In which things happen, or a simple sequence that tells a story.
Right. Right.
That brings in a memory aspect as well. But also, I mean, you could imagine a game in which the user's input is verbal.
Yeah.
So they're telling, they're naming things in the picture,
right,
and telling you what to do with them.
That's right. So it could be as simple as play this game at least 10-15 minutes every day.
Well, or every week, let's say. I mean,
or a few minutes.
Might be too much, but I mean, yeah, if people really, I mean, again, another point here though is that people are not all the same in their entertainment tastes. And so you would probably need a variety of different kinds of games to suit different tastes. And that, of course, makes the problem a little bit more complicated, because then you have to not just establish norms across pictures, but establish norms across games. But, I gave a talk about this stuff last fall at Apple Labs in Cupertino. And I mentioned the fact, some work that we've been doing on autism, where we had persuaded the head of the Center for Autism Research at Children's Hospital that having access to a very, very large body of shared data would really be important, because we were getting lots of interesting results from just 100 subjects. And so what he said was, gee, if we had 10,000 subjects, maybe we could really figure out what's going on. And so I quoted that, and a woman in the front row sort of furrowed her brow and raised her hand and said, 10,000? Why not 10 million?
Yeah, it's a rapidly increasing.
That's the way they think out there.
Yeah, rapidly increasing condition. I don't know, when is it typically diagnosed? Do you know?
When is what typically diagnosed?
Autism spectrum disease.
Oh, so that's a big problem, actually, because it's essentially never diagnosed before about the age of 1.5 or 2.
Okay.
And usually not until somewhat beyond that. But there are reasons to believe that there are actually symptoms pretty much from birth, but certainly at, say, 6 months.
So just making noises, not really language.
In terms of crying and babbling and comfort noises, and maybe gaze interaction with caregivers and other things. In fact, there's a research project, a multi-site research project that some people at Penn are involved with, that's going on now with respect to that. And the reason that's important, that might be important, is that there are behavioral interventions that are quite helpful in that case. And the earlier you bring them to bear, the better off everybody is. And so there's a belief that if you could diagnose accurately at 6 months or a year, that would be a lot better than diagnosing at 2 years or 3 years. But at the moment, we can't.
Right. Yeah, that's a huge application. So in conclusion, Mark, you have done obviously a lot of work in this area for a long time. We have more computing power, we have more memory, the infrastructure is getting bigger and bigger. Where do you think we will be, let's say 5 years from now? On two dimensions. One is, sort of the technology itself getting better, and the other is, from an application perspective, especially life sciences applications.
So I think the important thing is that for the life sciences applications, we don't actually need any new invention or any new technology. We just need data and research.
So it's already there. It's really
the abstract capability is there. The actual systems are not. And whether they're here in 5 years or not depends on on whether sort of anybody, whether people come forward to organize, fund,
and commercialize, so to speak.
and commercialize. Yeah. The commercialization, I think, will come pretty easy.
Yeah.
I don't think that's a problem. But at the moment, we don't have things to commercialize.
Right.
Now, there are lots and lots and lots of areas where the technology is not nearly as good as we would like it to be. And it's hard to know whether there's going to be rapid progress in that area or not.
Right.
So lots of people are pursuing ideas in what you might call new AI, which is to go beyond the sort of apply deep learning to an astronomically large training set.
Yeah.
And then hope it generalizes to the material that you want to apply it to, and are instead. So let me give one example. Suppose that we were trying to extract relevant features from the text fields, the free text fields in medical records.
Yeah.
So medical records contain quantitative information, numbers. They contain ordinal information. You know, this is stage 1, stage 2, stage 3. They contain binary information. This person does or doesn't have characteristic X.
Yeah.
But they also contain free text.
Right.
Where a doctor or a nurse or a social worker or somebody is writing in material in answer to a question. And we would very much like to be able to combine that free text information with the information in the other fields in epidemiological or other kinds of modeling.
Yeah.
The most obvious thing to do is just to throw in all the words as features.
Right.
And in general, that does not work well. Among other things, because of negation. It turns out that there are an amazing number of different ways to say that someone didn't exhibit any cardiac symptoms.
Right.
And so the word cardiac may or may not be relevant.
Yeah.
You know? Yeah. Now, with a human being who understands the area, you can explain what it is that you want them to annotate, the pieces of information you want them to pull out of the field. And that just takes a few minutes. You know, you maybe spend 10 minutes or 15 minutes going through some examples and making sure that they're doing it right. And then they do it. So they will have seen, you know, 10 or 15 or 20 examples.
Yeah.
We can't do that kind of conceptual parsing now with an automated system. We absolutely can do conceptual parsing of those free text fields, but we would need either a smart engineer coding away for a few months, or we would need lots of annotators producing 100,000 training examples, which we probably couldn't get because we don't have that many patient records from one hospital.
Right.
So anyway, that's an example of the kind of real artificial intelligence that is the ability to appropriately learn once you have the basis to adapt from a small number of examples.
Right.
And there is a lot of people work on adaptive learning, no question about it. But in areas like that, we're just not there yet.
Right.
So if there are breakthroughs in that area, then 5 years from now could be very different than today. But if there aren't, then it will be just like today, only more so.
Yeah, so that keeps the field interesting, at least for a while. So,
I think so.
Yeah, this has been great, Mark. Thanks so much for spending time with me, and good luck with all this research.
Okay, bye-bye.
Thank you.